Apollo 13. Apollo 13 was the seventh manned mission in the Apollo space program and the third intended to land on the Moon. The craft was launched on April 11, 1970 from the Kennedy Space Center, Florida, but the lunar landing was aborted after an oxygen tank exploded 2 days later, crippling the service module upon which the command module had depended. Despite great hardship caused by limited power, loss of cabin heat, shortage of potable water, and the critical need to make makeshift repairs to the carbon dioxide removal system, the crew returned safely to Earth on April 17, 1970, 6 days after launch. The flight passed the far side of the Moon at an altitude of 254 kilometers above the lunar surface, and 400,171 km from Earth, a spaceflight record marking the farthest humans have ever traveled from Earth. The mission was commanded by James A. Lovell with John L. Jack Swigert as Command Module pilot and Fred W. Hayes as Lunar Module pilot. Swigert was a late replacement for the original CM pilot Ken Mattingly, who was grounded by the flight surgeon after exposure to German measles. The story of the Apollo 13 mission has been dramatized multiple times, most notably in the 1995 film Apollo 13. According to the standard crew rotation in place during the Apollo program, the prime crew for Apollo 13 would have been the backup crew for Apollo 10 with Mercury and Gemini veteran L. Gordon Cooper in command. That crew was composed of Deke Slayton, NASA's Director of Flight Crew Operations, never intended to rotate Cooper and Isola to another mission, as both were out of favor with NASA management for various reasons. He assigned them to the backup crew simply because of a lack of flight-qualified manpower in the astronaut office at the time the assignment needed to be made. Slayton felt Cooper had no more than a very small chance of receiving the Apollo 13 command, if he did an outstanding job with the assignment, which he did not. Despite Isola's issues with management, Slayton always intended to assign him to a future Apollo Applications Program mission rather than a lunar mission, but this program was eventually cut down to only the Skylab component. Thus, the original assignment Slayton submitted to his superiors for this flight was. For the first time ever, Slayton's recommendation was rejected by management, who felt that Shepard needed more time to train properly for a lunar flight, as he had only recently benefited from experimental surgery to correct an inner ear disorder which had kept him grounded since his first Mercury flight in 1961. Thus, Lovell's crew, backup for the historic Apollo 11 mission and therefore slated for Apollo 14, was swapped with Shepard's crew and the original crew selection for the mission became Prime Crew. Backup Crew. Ken Mattingly was originally intended as the Command Module pilot. 7 days before launch, the backup Lunar Module pilot, Charlie Duke, contracted rubella from one of his children. This exposed both the prime and backup crews, who trained together. Mattingly was found to be the only one of the other 5 who had not had rubella as a child and thus was not immune. 3 days before launch, at the insistence of the flight surgeon, Swigert was moved to the prime crew. Mattingly never contracted rubella and was assigned after the mission as Command Module pilot to Young's crew, which later flew Apollo 16, the 5th mission to land on the Moon. The astronauts' mission Insignia was sculpted as a medallion depicting steeds of Apollo by Luman Martin Winter and was struck by the Franklin Mint. The Apollo 13 mission was to explore the Fra Mauro Formation, or Fra Mauro Highlands, named after the 80-kilometer diameter Fra Mauro crater located within it. It is a widespread, hilly selenological area thought to be composed of ejecta from the impact that formed Mare Imbrium. The next Apollo mission, Apollo 14, eventually made a successful flight to Fra Mauro. April 14, 1970 UTC. April 15, 1970, 21 minutes UTC, 137 nmi. April 17, 1970, 18 hours 7 minutes and 41 seconds UTC. Crew was on board the USS Iwo Jima 45 minutes later. The mission was launched at the planned time, 2:13:0 p.m. EST on April 11. An anomaly occurred when the second stage, center engine shut down about 2 minutes early. The 4 outboard engines and the third stage engine burned longer to compensate, and the vehicle achieved very close to the planned circular 100 nautical miles parking orbit, followed by a normal translunar injection about 2 hours later. The engine shutdown was determined to be caused by severe pogo oscillations measured at a strength of 68 grams and a frequency of 16 Hz, flexing the thrust frame by 3 inches. The vehicle's guidance system shut the engine down in response to sensed thrust chamber pressure fluctuations. Pogo oscillations had been seen on previous Titan rockets, and also on the Saturn V during Apollo 6, but on Apollo 13, they were amplified by an unexpected interaction with turbopump cavitation. Later missions implemented anti-pogo modifications that had been under development. These included addition of a helium gas reservoir to the center engine liquid oxygen line to damp pressure oscillations, an automatic cutoff as a backup, and simplification of the propellant valves of all 5 second-stage engines. The crew performed the separation and transposition maneuver to dock the CM Odyssey to the LM Aquarius, and pulled away from the spent third stage, which ground controllers then sent on a course to impact the Moon in range of a seismometer placed on the surface by Apollo 12. They then settled in for the 3-day trip to Fra Mauro. Approaching 56 hours into the mission, Apollo 13 was approximately 205,000 miles from Earth en route to the Moon. Approximately 6.5 minutes after the end of a live TV broadcast from the spacecraft, Hayes was in the process of closing out the LM, while Lovell was stowing the TV camera. Houston flight controllers asked Swigert to turn on the hydrogen and oxygen tank stirring fans in the service module, which were designed to destratify the cryogenic contents and increase the accuracy of their quantity readings. 2 minutes later, the astronauts heard a pretty large bang, accompanied by fluctuations in electrical power and the firing of the attitude control thrusters. The crew initially thought that a meteoroid might have struck the lunar module. Communications and telemetry to Earth were lost for 1.8 seconds, until the system automatically corrected by switching the high-gain S-band antenna, used for translunar communications, from narrowbeam to widebeam mode. Immediately after the bang, Swigert reported a problem, which Lovell repeated and clarified as a main B bus undervolt, a temporary loss of operating voltage on the second of the spacecraft's main electrical circuits. Oxygen tank 2 immediately read quantity 0. About 3 minutes later, the number 1 and number 3 fuel cells failed. Lovell reported seeing out the window that the craft was venting a gas of some sort into space. The number 1 oxygen tank quantity gradually reduced to 0 over the next 130 minutes, entirely depleting the SM's oxygen supply. Because the fuel cells generated the command and service module's electrical power by combining hydrogen and oxygen into water, when oxygen tank 1 ran dry, the remaining fuel cell finally shut down, leaving the craft on the command module's limited duration battery power and water. The crew was forced to shut down the CM completely to save this for re-entry, and to power up the LM to use as a lifeboat. This situation had been suggested during an earlier training simulation, but had not been considered a likely scenario. Without the LM, the accident would certainly have been fatal. The damage to the service module made safe return from a lunar landing impossible, so lead flight director Gene Kranz ordered an abort of the mission. The existing abort plans, first drawn up in 1966, were evaluated. The quickest was a direct abort trajectory, which required using the service propulsion system engine to achieve a 6,079 foot per second delta V.P3-14. Although a successful SBS firing at 60 hours ground elapsed time would land the crew 1 day earlier, the large delta V was possible only if the LM were jettisoned first P21, and since crew survival depended on the LM's presence during the coast back to Earth, that option was out of the question. P3-17. An alternative would have been to burn the SBS fuel to depletion, then jettison the service module and make a second burn with the LM descent propulsion system engine. It was desired to keep the service module attached for as long as possible because of the thermal protection it afforded the command module's heat shield. Apollo 13 was close to entering the lunar sphere of gravitational influence, which was the break-even point between direct and circumlunar aborts, and the latter allowed more time for evaluation and planning before a major rocket burn. B5. There also was concern about the structural integrity of the service module, P323, so mission planners were instructed that the SBS engine would not be used except as a last-ditch effort P3-14. For these reasons, Krantz chose the alternative circumlunar option, using the Moon's gravity to return the ship to Earth. Apollo 13 had left its initial free return trajectory earlier in the mission, as required for the lunar landing at Framoro. Therefore, the first order of business was to re-establish the free return trajectory with a 30.7-second burn of the DPS. The descent engine was used again 2 hours after Parasynthian, the closest approach to the Moon, to speed the return to Earth by 10 hours and move the landing spot from the Indian Ocean to the Pacific Ocean. A more aggressive burn could have been performed at PC+2 by first jettisoning the service module, returning the crew in about the same amount of time as a direct abort P3-20, but this was deemed unnecessary given the rates at which consumables were being used. The 4-minute, 24-second burn was so accurate that only 2 more small course corrections were subsequently needed. Considerable ingenuity under extreme pressure was required from the crew, flight controllers, and support personnel for the safe return. The developing drama was shown on television. Because electrical power was severely limited, no more live TV broadcasts were made. TV commentators used models and animated footage as illustrations. Low power levels made even voice communications difficult. The Lunar Module consumables were intended to sustain 2 people for a day and a half, not 3 people for 4 days. Oxygen was the least critical consumable because the LM carried enough to repressurize the LM after each surface EVA. Unlike the command and service module, which was powered by fuel cells that produced water as a byproduct, the LM was powered by silver zinc batteries, so electrical power and water were critical consumables. To keep the LM life support and communication systems operational until re-entry, the LM was powered down to the lowest levels possible. In particular, the LM's abort guidance system was used for most of the coast back to Earth instead of the primary guidance system, as it used less power and water. pp. 31733,40. Availability of lithium hydroxide for removing carbon dioxide presented a serious problem. The LM's internal stock of LiOH canisters was not sufficient to support the crew until return, and the remainder was stored in the descent stage, out of reach. The CM had an adequate supply of canisters, but these were incompatible with the LM. Engineers on the ground improvised a way to join the cube-shaped CM canisters to the LM's cylindrical canister sockets by drawing air through them with a soot return hose. NASA engineers referred to the improvised device as the mailbox. Another problem to be solved for a safe return was accomplishing a complete power-up from scratch of the completely shut-down command module, something never intended to be done in flight. Flight controller John Aaron, with the support of grounded astronaut Mattingly and many engineers and designers, had to invent a new procedure to do this with the ship's limited power supply and time factor. This was further complicated by the fact that the reduced power levels in the LM caused internal temperatures to drop to as low as 4 degrees C. The unpowered CM got so cold that water began to condense on solid surfaces, causing concern that this might short out electrical systems when it was reactivated. This turned out not to be a problem, partly because of the extensive electrical insulation improvements instituted after the Apollo 1 fire. The last problem to be solved was how to separate the lunar module a safe distance away from the command module just before re-entry. The normal procedure was to use the service module's reaction control system to pull the CSM away after releasing the LM along with the command module's docking ring, but this RCS was inoperative because of the power failure, and the useless SM would be released before the LM. To solve the problem, Grumman called on the engineering expertise of the University of Toronto. A team of 6 UT engineers, led by senior scientist Bernard Etkin, was formed to solve the problem within a day. The team concluded that pressurizing the tunnel connecting the lunar module to the command module just before separation would provide the force necessary to push the 2 modules a safe distance away from each other just prior to re-entry. The team had 6 hours to compute the pressure required, using slide rules. They needed an accurate calculation, as too high a pressure might damage the hatch and its seal, causing the astronauts to burn up, too low a pressure would not provide enough separation distance of the LM. Grumman relayed their calculation to NASA, and from there in turn to the astronauts, who used it successfully. As Apollo 13 neared Earth, the crew first jettisoned the service module, using the LM's reaction control system to pull themselves a safe distance from it, instead of the normal procedure which used automatic firing of the SM's RCS. They photographed it for later analysis of the accident's cause. It was then that the crew were surprised to see for the first time that the entire Sector 4 panel had been blown off. According to the analysts, these pictures also showed the antenna damage and possibly an upward tilt to the fuel cell shelf above the oxygen tank compartment. Finally, the crew jettisoned the Lunar Module Aquarius using the above procedure worked out at the University of Toronto, leaving the command module Odyssey to begin its lone re-entry through the atmosphere. The re-entry on a lunar mission normally was accompanied by about 4 minutes of typical communications blackout caused by ionization of the air around the command module. The blackout in Apollo 13's re-entry lasted 6 minutes, which was 87 seconds longer than had been expected. The possibility of heat shield damage from the O2 tank rupture heightened the tension of the blackout period. Odyssey regained radio contact and splashed down safely in the South Pacific Ocean, 21°3824 S 165°2142 W/21.64,000° S 165.36167° W/-21.64000-165.36167, southeast of American Samoa and 6.5 km from the recovery ship, USS Iwo Jima. The crew was in good condition except for Hayes, who was suffering from a serious urinary tract infection because of insufficient water intake. To avoid altering the trajectory of the spacecraft, the crew had been instructed to temporarily stop urine dumps, which forced them to invent ways of storing all urine for the rest of the flight. The Lunar Module and Service Module re-entered the atmosphere over the South Pacific between the islands of Fiji and New Zealand. The crew of Apollo 13 on board the USS Iwo Jima following splashdown. The Apollo 13 Lunar Module Aquarius is jettisoned above the Earth after serving as a lifeboat for 4 days. It re-entered Earth's atmosphere over Fiji and burned up during re-entry. Apollo 13 Service Module and Lunar Module as they entered Earth's atmosphere over the Pacific Ocean on April 18, 1970 between the Fiji Islands and Auckland, New Zealand. Apollo 13's damaged service module, as photographed from the command module after being jettisoned. Mission Control celebrates the successful splashdown of Apollo 13. The Apollo 13 crew talking with President Nixon on April 17, 1970. NASA Administrator Thomas Paine and Deputy Administrator George Low sent a memorandum to NASA Langley Research Center Director Edgar M. Courtwright on April 17, 1970, advising him of his appointment as chairman of an Apollo 13 review board to investigate the cause of the accident. The second memorandum to Courtwright from Paine and Low on April 21 established the board as follows. The board exhaustively investigated and analyzed the history of the manufacture and testing of the oxygen tank, and its installation and testing in the spacecraft up to the Apollo 13 launch, as documented in detailed records and logs. They visited and consulted with engineers at the contractors' sites and the Kennedy Space Center. Once a theory of the cause was developed, elements of it were tested, including on a test rig simulation in a vacuum chamber, with the damaged tank installed in the fuel cell bay. This test confirmed the theory when a similar explosion was created, which blew off the outer panel exactly as happened in the flight. Courtwright sent the final report of Apollo 13 review board to Thomas Paine on June 15, 1970. The failure started in the service module's number 2 oxygen tank. Damaged Teflon insulation on the wires to the stirring fan inside oxygen tank 2 allowed the wires to short-circuit and ignite this insulation. The resulting fire rapidly increased pressure beyond its 1,000 pound per square inch limit and the tank dome failed, filling the fuel cell bay with rapidly expanding gaseous oxygen and combustion products. It is also possible some combustion occurred of the mylar/captain thermal insulation material used to line the oxygen shelf compartment in this bay. The resulting pressure inside the compartment popped the bolts attaching the 13-foot Sector 4 outer aluminum skin panel, which as it blew off probably caused minor damage to the nearby S-band antenna. Mechanical shock forced the oxygen valves closed on the number 1 and number 3 fuel cells, leaving them operating for only about 3 minutes on the oxygen in the feed lines. The shock also either partially ruptured a line from the number 1 oxygen tank, or caused its check or relief valve to leak, causing its contents to leak out into space over the next 130 minutes, entirely depleting the SM's oxygen supply. The board determined the oxygen tank failure was caused by an unlikely chain of events. Tanks storing cryogens, such as liquid oxygen and liquid hydrogen, require either venting, extremely good insulation, or both, in order to avoid excessive pressure buildup due to vaporization of the tank's contents. The service module oxygen tanks were so well insulated that they could safely contain supercritical hydrogen and oxygen for years. Each oxygen tank held several hundred pounds of oxygen, which was used for breathable air and the production of electricity and water. The construction of the tanks made internal inspection impossible. The tank contained several components relevant to the accident. The heater and protection thermostats were originally designed for the command module's 28-volt DC bus. The specifications for the heater and thermostat were later changed to allow a 65-volt ground supply, in order to pressurize the tanks more rapidly. Beechcraft, the tank subcontractor, did not upgrade the thermostat to handle the higher voltage. The oxygen shelf carrying the oxygen tanks was originally installed in the Apollo 10 service module, but was removed to fix a potential electromagnetic interference problem. During removal, the shelf was accidentally dropped about 2 inches because a retaining bolt had not been removed. The tank appeared to be undamaged, but a loosely fitting filling tube was apparently damaged, and photographs suggested that the closeout cap on the top of the tank may have hit the fuel cell shelf. The report of the Apollo 13 Review Board considers the probability of tank damage during this incident to be rather low. After the tank was filled for ground testing, it could not be emptied through the normal drain line. To avoid delaying the mission by replacing the tank, the heater was connected to 65-volt ground power to boil off the oxygen. Lovell signed off on this procedure. It should have taken a few days at the thermostatic opening temperature of 27 degrees C. When the thermostat opened, the 65-volt supply fused, its contacts closed, and the heater remained powered. The board confirmed by testing that the thermostats welded themselves closed under the higher voltage. This raised the temperature of the heater to an estimated 540 degrees C. A chart recorder on the heater current showed that the heater was not cycling on and off, as it should have been if the thermostat was functioning correctly, but no one noticed it at the time. Because the temperature sensor was not designed to read higher than the 27 degrees C thermostat opening temperature, the monitoring equipment did not register the true temperature inside the tank. The gas boiled off in hours rather than days. The sustained high temperatures melted the Teflon insulation on the fan power supply wires and left them exposed. When the tank was refilled with oxygen, it became a bomb waiting to go off. During the cryostor procedure, fan power passed through the bare wires, which apparently shorted, producing sparks and igniting the Teflon. This in turn boiled liquid oxygen faster than the tank vent could remove it. In June 1970, the Courtright report provided an in-depth analysis of the mission in an extremely detailed 5-chapter report with 8 appendices. It included a copy of established NASA procedures for alleviating high pressure in a cryogenic oxygen tank, to include. This procedure was designed to prevent hardware failures so that the lunar landing mission could be continued. The Mission Operations Report Apollo 13 recounts how the master caution and warning alarm had been turned off for a previous low-pressure reading on hydrogen tank 2, and so it did not trigger to call attention to the high oxygen pressure reading. Oxygen tank 2 was not the only pressure vessel that failed during this mission. Prior to the accident, the crew had moved the scheduled entry into the Lunar Module forward by 3 hours. This was done to get an earlier look at the pressure reading of the supercritical helium tank in the LM descent stage, which had been suspect since before launch. After the abort decision, the helium pressure continued to rise and mission control predicted the time that the burst disk would rupture. The helium tank burst disk ruptured at 1:08:54, after the lunar flyby. The expulsion reversed the direction of the passive thermal control roll. While the investigation board did recreate the oxygen tank failure, it did not report on any experiments that would show how effective the cryogenic malfunctions procedures were to prevent the system failure by de-energizing the electrical heater and fan circuits. The oxygen tank was redesigned, with the thermostats upgraded to handle the proper voltage. The heaters were retained since they were necessary to maintain oxygen pressure. The stirring fans, with their unsealed motors, were removed, which meant the oxygen quantity gauge was no longer accurate. This required adding a third tank so that no tank would go below half full. All electrical wiring in the power system bay was sheathed in stainless steel, and the oxygen quantity probes were changed from aluminum to stainless steel. The fuel cell oxygen supply valves were redesigned to isolate the Teflon-coated wiring from the oxygen. The spacecraft and mission control monitoring systems were modified to give more immediate and visible warnings of anomalies. Because Apollo 13 followed the free return trajectory, its altitude over the lunar far side was approximately 100 km greater than the orbital altitude on the remaining Apollo lunar missions. The Moon was almost at apogee during the mission, which also increased the distance from the Earth. The combination of the two effects ensures that Apollo 13 holds the absolute altitude record for a manned spacecraft, reaching a distance of 400,171 km from Earth on 7:21 p.m. EST, April 14, 1970. The A-7L spacesuit intended to be worn on the lunar surface by Lovell would have been the first to feature red bands on the arms, legs, lunar EVA helmet assembly, and the life support backpack. This came about because mission control personnel watching the video feeds of Apollos 11 and 12 had trouble distinguishing the astronauts while both had their helmet sunshades down. The red bands were used for the remaining Apollo flights, the Space Shuttle program, and in the International Space Station. The Apollo 13 mission was called a successful failure by Lovell, because of the successful safe return of the astronauts, but the failed lunar landing. It has also been termed NASA's finest hour. President Nixon awarded the Presidential Medal of Freedom to the crew and the Apollo 13 mission operations team for their actions during the mission. The cold cathode gauge experiment, which was part of the ALSEP on Apollo 13, was never flown again. It was a version of the cold cathode ion gauge which featured on Apollo 12, Apollo 14, and Apollo 15. The CCGE was designed as a standalone version of the CCIG. On other missions, the CCIG was connected as part of the superthermal ion detector. Because of the aborted landing, this experiment was never deployed. Other experiments included on Apollo 13's ALSEP included the heat flow experiment, the passive seismic experiment, and the charged particle lunar environment experiment. The original lunar plaque affixed to the front landing leg of Aquarius bore Mattingly's name, so a replacement plaque with Swiggert's name was carried in the cabin, for Lovell to place over the other after he descended the ladder. He kept the plaque as a souvenir. In his book Lost Moon, Lovell stated that, apart from the plaque and a couple of other pieces, the only other memento he possesses is a letter from Charles Lindbergh. The Apollo 13 crew patch featured 3 flying horses as Apollo's chariot across space. Given Lovell's Navy background, the logo also included the mottos Ex Luna, Science NTIA, borrowed from the U.S. Naval Academy's motto, Ex Science NTIA Tridens. The mission number appeared in Roman numerals as Apollo 13. The patch did not have to be modified after Mattingly's replacement since it is one of only 2 Apollo mission insignia, the other being Apollo 11, not to include the names of the crew. It was designed by artist Luman Martin Winter, who based it on a mural he had done for the St. Regis Hotel in New York City. The mural was later purchased by actor Tom Hanks, who portrayed Lovell in the movie Apollo 13, and now is on the wall of a restaurant near Chicago owned by Lovell's son. Despite Apollo 13's failure to land on the Moon, several experiments were conducted successfully because they were initiated before or conducted independently of the oxygen tank explosion. As a joke following Apollo 13's successful splashdown, Grumman Aerospace Corporation pilot Sam Greenberg issued a tongue-in-cheek invoice for $400,540.05 to North American Rockwell, Pratt & Whitney, and Beech Aircraft, Prime, and subcontractors for the CSM, for towing the crippled ship most of the way to the moon and back. The figure was based on an estimated 400,001 miles at $1 per mile, plus $4 for the first mile. An extra $536.05 was included for battery charging, oxygen, and an additional guest in room. A 20% commercial discount, as well as a further 2% discount if North American were to pay in cash, reduced the total to $312,421.24. North American declined payment, noting that it had ferried 3 previous Grumman LMS to the moon with no such reciprocal charges. The command module shell was formerly at the Musée de l'Art de l'Espace, in Paris. The interior components were removed during the investigation of the accident and reassembled into boilerplate BP 1102A, the water egress training module, and were subsequently on display at the Museum of Natural History and Science in Louisville, Kentucky, until 2000. The command module and the internal components were reassembled, and Odyssey is currently on display at the Cosmosphere in Hutchinson, Kansas. The Lunar Module burned up in Earth's atmosphere on April 17, 1970, having been targeted to enter over the Pacific Ocean to reduce the possibility of contamination from a SNAP-27 radioisotope thermoelectric generator on board. Intended to power the mission's ALSEP, the RTG survived re-entry and landed in the Tonga Trench. While it will remain radioactive for several thousand years, it does not appear to be releasing any of its 3.9 kg of radioactive plutonium-238. Lovell's lunar spacesuit helmet, one of his gloves, and the plaque that had been intended to be left on the moon are on exhibit at the Adler Planetarium in Chicago, Illinois. The Apollo 13 SIVB with its instrument unit was guided to crash onto the lunar surface on April 14, providing a signal for the Apollo 12 passive seismic experiment. A recording of the Apollo 13 SIVB's impact on the lunar surface as detected by the Apollo 12 passive seismic experiment. Crater left by the SIVB's impact. LM armrest on display at the App Hole.